Hello, this is a video on general exponential functions, by which I mean a raised to the r power. That's what this a hat r means, a raised to the r. You might come across that. Uh, so the general exponential function, and I'm following James Stewart's Calculus 6th edition. He has a chapter 7 in there. A lot of it deals with exponential, logarithmic, those sorts of functions. And so the asterisk refers to the fact that he kind of does two versions of the same material, kind of Wayne's World. Let's do it again. Um, and the second version with the asterisk is a more rigorous approach. So they're more kind of proofs. And that really shows up in this slide, because if we have an exponential function with base a, so like a to the r, this is an exponential function. An exponential function is one where the base is a constant and the variable is the power. Now the power function is where the base is a variable and the power is a constant. But an exponential function has a constant as a base and then a power that's a variable. Okay, now this is a strange way to define a to the r power. He defines it here as e to the natural log of a raised to the r power. That's kind of bizarre, but the reason he does it is so that it works in various proofs and so forth. So we can bring the r into the power. It's one of the rules with the natural base there, e 2.718281828, etc. So this is the way he's going to define a to the r in this way, which means that a to the r equals e to r times the natural logarithm of a. Who knew? I mean, it works, but because of the cancellation, right? Because e to the natural log cancels out, and you're left with a to the r. So it all works. It's just kind of bizarre. But what this allows us to see fairly easily, thereby, is that the natural log of a to the r power is going to be the natural log of this, natural log of e to r natural logarithm of a. And we know that this is going to cancel out, right? And we're going to be left with r natural log of a. So by defining it this way, we discover that the natural logarithm of a to the r is going to be r times the natural logarithm of a. So that's why they did it. That's why he's defined it this way, so that we know what the natural logarithm of an exponential function is. The natural logarithm of an exponential function is going to be the power times the natural logarithm of the base. All right, there you have it. Now the laws of exponents apply for these exponential functions just like they applied to the natural logarithm. So a base to the x plus y power is the same as multiplying a to the first times a to the second. All right. And if we have a minus a to the x minus y, it's going to be a to the x on the top divided by a to the y on the bottom. Again, these should be fairly, familiar to you, I think. Or a to the x raised to the y is the same as a to the x times the y, right? And then lastly, if you have ab raised to the x, that's the same as a to the x times b to the x. And because the way he's defined it, he gives proofs for a couple of these, and then the exercises, I think, ask you to do the other proofs. That's all in Stewart. Many more proofs in this asterisk approach, it seems to me. Okay, now let's look at the way some of these things look. So a to the x, if a, that is, if the base is greater than 1, then the limit as a to the x approaches infinity is infinity. So it goes up like this. Remember that the natural logarithm function kind of goes like this. It's but this power function is the inverse, and it goes like this. So the limit as you approach negative infinity, you can see, is approaching y equals 0. So this is the way the exponential function looks if if the base is greater than 1. What if the base is in between 1 and 0? well, then it's going to look almost the opposite. Then as x approaches infinity, we approach 0. And as x approaches negative infinity, we approach infinity. So this is for the exponential function a to the x when it's in between 0 and 1. Of course, both of them go through 1, go through y equals 1. Why is that? Because when y equals 1, x equals 0. So anything to the 0 power, right, is 1. And so there's also a picture in Stewart in which he shows how the higher, the higher the base, the steeper it gets quicker, the more quickly it gets steep. So be sure and look at that diagram in the book. Okay, what about the derivative of the exponential function? Well, the derivative, and this is again, if you don't want to know the proof, this is what you need to know. So you need to know that the derivative of a to the x is a to the x times the natural logarithm of a, times the base, that is. The proof of this is as such. So he has defined, right, a to the x as e to the natural logarithm of a raised to the x, because they cancel out each other, right? And then you can pull the x out of a to the natural logarithm of a to x. You can pull the x down into the coefficient, or to the front, which is again shown in previous videos. Okay, so this is basically the same thing as this. We've just e to the natural logarithm it, which cancels it out, right? Like the string where you put your hand in, it's gone. And so once I've done this, I know how to take the derivative from, again, previous videos that are asterisked. This e x to the natural logarithm a pulls out of the front, and then I just take the natural logarithm of the exponent. Well, x is the variable here. The natural logarithm of a is a constant. So basically, it becomes this again. Once we then we cancel out e in the natural logarithm, we're left with a to the x again, and then x becomes 1 when you take the derivative of it, and you're just left with a to the x times the natural logarithm of a. So this is, if you didn't get the proof, this is what you need to know, that the derivative of the exponential function is the exponential function times the natural logarithm of the base. So this is one of the main things to get from this video. You should know the basic curves and the laws, and you should know that the natural logarithm of a to the r is r times the natural logarithm of a. Okay, so one more thing. We now come to the integral of the exponential function, which is basically just the reverse of this. The integral of it is going to be whatever that, if you take the derivative of it, you're going to end up with a to the x. So you're going to have the natural logarithm of a on the bottom, because when you take the derivative of it, then natural logarithm of a and natural logarithm of a will cancel out, and you'll be left with a to the x again, right? Plus a constant. A cannot equal 1, because then you would have a 0 in the denominator. All right, so this is some basically things to know about exponential function. Know that this is the integral of the exponential function. Know that this is the derivative of the natural logarithm function. Know what the basic graph looks like when the base is between 0 and 1, and know what the basic graph looks like when a is greater than 1. Know the basic rules of laws of exponents, which I think you probably learned in pre-calc. And then know that the natural logarithm of an exponential function is the power times the natural logarithm of the base. So this has been a video on general exponential functions.